Hello everybody, my name is Dylan Holst, and I am a graduate student in the Wickens group at UW-Madison. We're a synthetic methodology group. In our group we like to use alternative energy inputs such as light and electricity to drive the discovery of new organic transformations. And so today I'll be talking about a recent paper that we published in JACS, a regiospecific Alkene Aminofunctionalization reaction via a Electrogenerated Dielectrophile. So our group has been really interested in alkene functionalization, and in particular we're really excited by the concept of alkene heterofunctionalization, a reaction in which you can install two different groups across an alkene. We think this reaction is super powerful because you can take alkenes, which are really simple and abundant starting materials, and transform them into highly complex structures in a single step. And in particular, we were really interested in this dielectrophile strategy for alkene heterofunctionalization, and in this type of approach you would create a dielectrophile directly from the alkene, which then could be intercepted with two distinct nucleophiles in order to enable alkene heterofunctionalization. We think that this approach would be really nice because it could enable the construction of these really complex structures from pretty simple and abundant nucleophiles as coupling partners. So this dielectrophile strategy does appear to be somewhat straightforward, but there's actually a series of problems that have hampered classic electrophiles such as dihalides being used in this manner. The first one is elimination. The nucleophiles that we're interested in are often basic enough to render these elimination reactions faster than the substitution reactions. There's also a regioselectivity issue. Of course, in the dielectrophile there's two positions that can be substituted, so once you add the second nucleophile, you get a mixture of products which is going to be certainly difficult to separate from each other. Final problem is this iterative addition problem. These nucleophiles can add to the dielectrophile once, so what's stopping them from adding the second time, right? So you can often get these homofunctionalization products, which can be also difficult to separate from your desired molecule. So we realized that we needed to develop a new dielectrophile itself that possessed the inherent selectivity profile needed to render this heterofunctionalization manifold possible. So previously our group had described the formation of dicationic adducts with a combination of terminal alkenes, thianthrine, and anodic oxidation. These adducts, whether you either have mono or bis adducts, are able to undergo productive aziridination reactivity simply via the addition of a primary amine and base. So we're really excited by these dielectrophiles because they appear to be unique in comparison to classic dielectrophiles. The corresponding dibromide was unable to undergo aziridination and instead suffered from the elimination pathway that I mentioned previously. So we were really excited to try out these thianthrinium-based dielectrophiles in this new heterofunctionalization context to push their reactivity further. So following a series of nucleophile studies, we discovered that the choice of potassium phthalimide as a nucleophile resulted in a selective single addition to generate an intermediate alkyl sulfonium salt in perfect regioselectivity. A divided electrochemical cell is used. Thianthrine is added to the anodic chamber of the cell, followed by our electrolyte, potassium hexafluorophosphate. Then the electrodes are added, which is a nickel foam cathode and an RVC anode. Solvent is added to both sides of the cell. The alkene as starting material is added, followed by trifluoroacetic acid, which is our counter reaction. Once the reagents are added, a constant current is applied, and the alkene is transformed into the mixture of two adducts via anodic oxidation of thianthrine. The pink-purple color that you can see coming off the electrode is the thianthrine radical cation that is generated via single electron oxidation at the anode. This species reacts with the alkene to generate the two adducts that we observe. So following the electrolysis, the adducts have been fully built up, and then we add our nucleophile potassium phthalimide. What we'll see is pretty high yield of the corresponding phthalimidosulfonium salt intermediate as a single regioisomer. At completion of this reaction, the reaction mixture can be filtered and then redissolved into DCM. The salt is easily then precipitated via the addition of ether as an anti-solvent, resulting in this nice white solid coming out of solution that we can just filter and then isolate as a solid. We see this as actually a new aminofunctionalization platform where now nucleophiles such as azide, thiolate, and even others, including amines, sulfonamides, and carboxylic acids, could substitute the intermediate to generate the new vicinally substituted molecules. Additionally, we really wanted to target a fully one-prot procedure for a more streamlined and practical procedure. We targeted alkene diamination for this context using two distinct amine sources, given the classic challenges with this type of transformation, and we found that various amines, both cyclic and acyclic, were viable for this reaction. We were able to generate a wide range of now differentially diaminated products in high yield. So overall, we're really excited about this as a potential new paradigm in regioselective alkene heterofunctionalization. While in this case, we leverage this unique dielectrophile selectivity profile for platform alkene aminofunctionalization, we think that these studies lay the foundation for the development of a wide array of different alkene heterofunctionalization reactions, and we're really excited to explore it further.